P is bigger than 0, then G is abelian. We can mostly just discuss the case where we're looking at some sort of discrete symmetry, Zn. And so here by Zn, I mean Zn is a subgroup of V1, which are generated by e to the 2 pi I over n. So if we call this element x, then all of the group elements are it's multiplicative under x. So you have x, x squared, x to the third, etc. up to x to the n minus 1 and 1. This is the group. Okay, so the reason why I want to talk about discrete symmetries is because all of the sort of analysis I gave you to derive all the higher group symmetries don't apply. So for discrete symmetries, there's generally no current. And that's essentially what we use to derive everything, and so if you don't have a current, then you're screwed. But I tried to formulate everything in a way that it's hopefully somewhat obvious how all of the global symmetries act. So, as I said on the previous days, if you have some higher form symmetry, you have some symmetry defect operator, and you can just treat G as being some element of your group, and sigma is the dimension, has the correct dimension for the P form global symmetry, and then you just have charged operators of dimension P, and you have the symmetry defect operators that enact the symmetry by linking. And this is just a general, we derived this using the current algebra, but this is just a general feature of how symmetries work in quantum field theory. So this,
Daniel, just to make sure, like, so actually this generalization to higher form symmetries and higher dimensional operators, how they act on each other, is really the only thing that seems to be changing is the dimensions and the codimensions. The action is otherwise just by a phase, multiplication of the operator by a phase with the charge.
Yes, that's right.
And so it's actually simple.
Yes, it's actually very simple, that's right. And so essentially the point is that we talked about this as a general group, even though we assumed that G was continuous, but this also, the structure also works for G discrete as well. So that's cool. But all of the sort of interesting analysis that you can do with higher form symmetries requires you to understand what it means to turn on a background gauge field. So say we want background gauge fields. But now we run into the problem of what does it mean to have a gauge field for a discrete global symmetry, or for a discrete symmetry generally at all. Yeah, so for example, if you tried to just write down some Zn gauge field, something like, for example, for a zero form Zn symmetry, you might try to write down a one form gauge field. Then you might ask, what is a discrete gauge form? What does a discrete gauge transformation look like? You might want to say it's G inverse dG. But if G is a discrete value, what does it mean to take its derivative? So this is the feature that I want to talk about today. So yeah, so there's sort of two ways we can think about. Let's just say it's Zn gauge theory. There's two ways we can think about Zn gauge theory. I first want to tell you the math version, and then I'll tell you the physics version. So the math version is sort of based on all of our discussion we had yesterday. One of the things I had told you is that we can think of a Zn gauge theory as this space that I described yesterday. It's principal bundle where now you have Zn copies, you have n copies of your space-time manifold, and the different copies can be fibered in a non-trivial way. And so this is something formal you can write down, but really what we want to know is how do you write down a gauge field for it. So as I said yesterday, one of the ways you can think about it is that for any curve, gamma, you need the exponential of a connection to be valued in your group. So in this case, it's Zn. The trick that we want to use here is that Zn is a subgroup of U1. So one way we can think about Zn gauge theory is just imagine we have a U1 gauge theory, and we just restrict ourselves to the Zn subgroup. So what I'm saying now is that, so take some U1 gauge field A, it's like a photon, and what this tells you is that there's a very strong restriction on the types of gauge fields you can have, but you can still think of this as a U1 gauge field, and that's totally fine. But this equation here has a very strong consequence. So imagine we have our manifold here now. And maybe it has some weird topology, but that doesn't matter. And let's imagine we take some curve gamma here, which is contractible. So that means it lives on the boundary of a disk. So if you want, you could think about squeezing gamma to a point. So now we have this, sorry, I'm going to get rid of this 2 pi because that's the standard convention. So if we integrate A1 along this curve gamma, this is in Zn. So what I mean by that is that this is generally equal to e to the 2 pi I times integer k divided by n. Now we can use the fact that for a U1 gauge field, the field strength is dA1. And now using Stokes' theorem, we can relate this integral here. It's the same thing as the integral, no longer closed, of the field strength over this disk. Good. But now, since gamma is contractible, you can think about squeezing it until you get all the way to a point. But we know that this is discrete. So that means that as you think about squeezing gamma to a point, this can't jump. Or if it did jump, it would have to jump discontinuously. And that would not be a U1 gauge field, not a smooth U1 gauge field. So what that means is that actually this has to be equal to 0. Because when you get to a point, you're integrating over nothing, and you can't get the integral of nothing is equal to something. So that implies it's actually equal to 1. And that tells you that the integral of f over any disk is equal to 0. And so this is called a flat gauge field. Yeah, so okay, I'm going to put this in quotation marks because it's not exactly true. Actually, the exact correct statement is that this is let's say it's true for any d that's contractible like this.
Daniel, to make sure I understand. So the difference with a continuous symmetry will be that you can deform continuously the value of A as you go, right?
That's right. Yeah, exactly. Yeah, this restriction implies that the gauge field is 0, integrates to 0 over any contractible disk. Cool. So that's interesting. And essentially the point is that So yeah, so now you'd ask, is there actually anything that's non-trivial at all? And the answer is yes, because if there's any curve here that you cannot contract, for example, I drew a two-dimensional manifold roughly. So if you were trying to integrate the gauge field along this argument would not work, and this could be non-zero. So in this sense, Z and gauge fields are somewhat tautological. And essentially the reason is that this equation has a lot of physics in it. What it implies is that there's no propagating degrees of freedom.
Is this not like the toric code that's a Z2 gauge theory?
Yes. Yeah, the Z, right. The toric code is an example of a Z2 gauge theory. That's much more formal driven than this. Yeah. Okay. So now I want to just tell you, I guess, one more thing, and then I'm going to give you a notation dump, just because most of the literature doesn't talk about fields this way. So here we use the fact that on any disk, the field strength is 0. But it's not true that the integral of f on any closed manifold, again, for example, on an S2, this is in general can be non-zero. In fact, it has to be 2 pi times an integer. And this is actually just the consequence of the fact that you have a U1 field strength. So U1 gauge fields has the integral of f is it is 2 pi times an integer. This is generally true. So what happens when you go to a Zn gauge field is that it's not 2 pi times any integer. There's actually only a Zn amount of information in a Zn gauge field. So it's 2 pi, it can be, yeah. So 0, 2 pi, up to 2 pi times n minus 1. So in other words, integral of f over 2 pi is valued in Zn. So a lot of discrete gauge theory is discussed in a very mathematical perspective. And I just want to give you a quick notational comparison. So, yeah, so I hope it's somewhat clear that this condition does not is separate from this condition. And it's just because you are writing a U1 field strength, or a U1 gauge field. In general, you sort of don't have any control over U1 gauge field, U1 field strengths if you specify their holonymies. That's sort of a deep statement that's very difficult to prove, but it's true, so I don't want to.
What is the statement?
The statement is, if I tell you a connection by specifying all of the possible holonymies, the field strength is not necessarily 0. Like, you cannot fix it to be 0. And that has to do with homotopy theory. So we'll just not discuss that. But so, right, so as I was saying, people usually discuss things, instead of in terms of U1 gauge fields, they talk about it in terms of these sort of, I'm just going to say it's the math convention. So they often discuss a Zn gauge field A in terms of some, essentially it's a 1 form. And the integral of A is equal to, from 0 root n minus 1. And this is different than this statement because essentially this it tells you that it's in Zn, but it can be up to k plus n, for example. So there's this redundancy where you're allowed to shift the holonomy by 2 pi times an integer. So, so for U1 gauge field, you're allowed to shift A1 to A1 plus B lambda, as we know. This is our gauge redundancy of a U1 gauge field. And you're allowed to pick a lambda so that the integral of d lambda on some S1, for example, is integer value. So that's why I talked about in terms of the exponential holonomy. But in the math literature, they often like to say, I don't care about U1 gauge fields. I just say this is literally equal 0 to n minus 1. And in that convention, the field strength of this is identically 0. But they have some notion of the field strength, even though it has no field strength. This is called the Bach-Stein map. And to describe the Bach-Stein map, I want to actually relate this convention to, we'll call this the physics convention. So the physics convention is that A is 2 pi over n times A, or at least that their integrals match. And the Bach-Stein takes A1, and it gives you what looks like a field strength, where the integral of F2 is similarly 0 through n minus 1 value. And essentially the point is that this field strength is actually the same as this. So I presented this in a way that looks totally trivial, but the formal definition of this is super complicated. And people often get very confused about it. So that's why I think it is best to just work in what we'll call the physicist notation convention. And so
what is that data doing?
This is the Bach-Stein. So the Bach-Stein map takes you from, is essentially, if you take your Zn gauge field, it gives you a field strength, even though it's has no field strength. People just call this the Bach-Stein, but it really is physically the field strength. Because what you have to do in order to define this is actually what people do is you say, I start here, and then I define this physicist A1, and then I compute its field strength. Okay. And then I do this reformulation, and that's how you define it. So the point is that you should always just start this way, and then it has a field strength and everything's totally fine.
Okay.
Sorry. So is there any mathematical formal problem with the physics notation, or is just that they like prepare it?
Right. So there are a few things that are clearer in the math convention, but I think that I don't think it outweighs the benefits of using the physics notation.
So it's just historical?
I think so. I'm being recorded, so I don't want to say anything too bad. Yeah. But anyways, so there's a lot of nice properties by using the math convention. And so one of the properties of the fact that this is working in modular arithmetic. So it's Zn valued. So when you go from U1 gauge fields to Zn gauge fields, you essentially replace the wedge product with what's called the cup product. So for example, I would write this field strength, or this differential form of the U1 gauge field. This becomes, okay, maybe I'll put some. This, when you sort of untangle all of the definitions here, that becomes A1 cup F2, and then there's there's a 2 pi here that cancels this 2 pi, I think. and you get 2 pi over n times n. So, anyways, I just think it's good to know that essentially you just do this replacement when you go from continuous gauge fields to discrete gauge fields. Okay, so that's all nice and formal, but I promise you that there's a physicist way of thinking about this.
I just want to say,
Yes.
Did you just call it the cup?
This is the cup product. Yes.
Oh, yes.
So this is the wedge product. This is called the cup product. And the cup product gets infinitely complicated as well. Or it's as complicated as you like it to be. There's actually an infinite number of cup products. But we don't want to talk about those. Okay. So now I'll give you the real physicist version of Zn gauge theory. So one of the biggest, an important thing when you're learning quantum field theory is the Higgs mechanism. And so as we know, the Higgs mechanism is a way that you start with some G gauge theory, and you break it to some subgroup H by taking some scalar field phi that has some charge under G, and then you allow it to have a non-trivial pattern. Okay. Clearly this is important for the Higgs particle. But I'm going to tell you a nice way that you can describe the Zn gauge theory by using the Higgs mechanism. So again, I'm going to start with a U1 gauge theory, and I'm going to break it to a Zn gauge theory by condensing some scalar field. So I like to work in 4 dimensions, because that's where I live. And so we're going to take a U1 gauge theory, so electromagnetism, plus a scalar field with charge n. Okay, so you can write down the action. Here's the kinetic term for the field, for the gauge field, and then you can just take the covariant derivative of phi squared. So another kinetic term. And now we're going to give phi a potential. And I'm going to just pick this to be, I guess is usually called the Mexican potential. Should think of a better name for that. Very good. So the reason why I'm picking phi to be charge n is the following. So for it to be charge n, what I mean is that under a gauge transformation is d I alpha, phi transforms to e to the I n alpha times phi. So if alpha is 2 pi over n times an integer k, then phi is inverted. Right, so in other words, there's a Zn subgroup of the gauge group that phi is uncharged under. So when we go from the UV to the IR, this potential causes the Higgs field to condense. Literally equal to E squared. And since, in this, right. I don't know which year it is. But anyway, so if you, there's a process that you can do called full evasion, and you can you can re-express it as a 2-form gauge field. And the way you do that is you construct, essentially, these 2 fields are linked by an equation of motion, which is d phi is equal to star of d p2. And so the reason why this works is because now the equation d squared phi is equal to 0 is the equation of motion for B2, D star B2 is equal to 0, which is the same thing as box B2 0. All right. And the equation of motion D star D phi is 0, implies the Bianchi identity, D squared B2 equals 0. So this is one way you can dualize this. And there's a nice prescription of how to do it, but it's not super important for what I'm going to say. So what it turns out is that when you start from this charge n abelian-Higgs model and you condense the scalar field, you flow to this IR model called BF theory. And here, the action is given by this. It's very simple. And what's nice about it is it's topological. The way to see that is there's no metric dependence here, because the wedge product has no metric dependence. The exterior derivative has no metric dependence because of the anti-symmetrization. And this entire theory is topological. So how can we see that it's a ZN gauge theory? So there's two ways. One is sort of implicit, one is explicit. So let's do the implicit one first. So the ZN gauge theory has, So for a ZN gauge field, the holonomy being valued in ZN tells you that you actually have n types of Wilson lines going back down. Because if you take a Wilson line and try to look at the charge n1, it would necessarily have be 0 because of this condition. So I'm saying that if you put an n here, you get rid of this n, and it's always trivial. So Cn implies that there is some fundamental Wilson line, and then you can take a charge, the one Wilson line squared, up to charge one Wilson line to n minus 1, and these are all the possible Wilson lines. In this theory, there are exactly n Wilson lines. The Wilson line is given by, well, the charge one Wilson line is the charge one Wilson line. And the way to see that there's only n of these, or there's only n minus 1 of these, is that there's actually a Zn one-form symmetry. And here the symmetry defect operator is what looks like sort of a Wilson line for V2. So this, people may not have seen an action where the kinetic term is sort of off diagonal like this before, or it's not like the field's derivative of the field squared. So I'll just tell you what it does. So, and essentially it turns these lines into the symmetry defect operator. The point is that if you link these two, and you can try to unlink them since it's topological, you find that, so this is Wilson 1, this is G, you find that there's exactly this G dot W action. And the way to see that is that the insertion of the Wilson line the insertion of the Wilson line here, you can think of in the path integral as adding a term to your action, which is I integral of A times a delta function. And now the equation of motion for A becomes n over 2 pi times B2 is delta of x. And so what you find is that B2 has this 1 over n sort of flux. So that what I mean by that is that if you integrate B2 around a linking two-dimensional manifold, then you'll get this, you'll exactly pick up this phase, which is 2 pi over n. And so, and then when you unlink it, this delta function is not activated, and so that's exactly how you see this action. Okay. So I think the last thing I want to say is you can actually show that this is explicitly as the n-gauge theory.
So this A is a 1 form, right?
Yes.
And delta is a what, 3 form?
It's a 3 form, yeah.
But V2 is a 2 form.
Sorry, this is E here. Yeah, good. Okay. Okay, I guess maybe there's 2 comments I want to make. So one is, what is this theory? What is, you know, I started with some nice physical theory and I got to give you some topological nonsense. In this theory, the Wilson line comes exactly from the Wilson line of your U1 gauge theory. But this B2 is kind of weird. What's happening is that, so let's just look at a one of these vertical B2s. So since B2 is 2-dimensional, you can think of this as some spatial vortex. And what happens is that when you condense the scalar field here, you actually are allowed to have what are called ANO vortices. So it gives Brikasov, Nielsen, Olesen vortices. And this is exactly what happens in a type 2 superconductor. What's happening is that you are allowed to wind the Higgs field around the base of your Mexican half potential. And then, so that gives you the vortex. But then the question is, why does that have some sort of non-trivial linking with the Wilson line? And what happens is that since this field is actually charged, this vortex, so here, let me draw a picture as I'm saying it. So here we're saying that the Higgs field, phi winds around this core of this vortex. But since the phi field is charged, what it looks like is you have some electrically charged particle going in a circle. And what that does is it generates a magnetic field going through the core here. So here's this magnetic flux. And this is exactly what happens in a type 2 superconductor. Except it usually happens the other way around. If you have some slab of superconductor, usually you give it a magnetic field, and what happens is the Higgs condensate will rotate in order to try to cancel it until it gets too big, and then it rotates to let it through. So this is yeah. So that's what this is, and the reason why it has some winding with the Higgs field or with the Wilson lines, we'll draw it this way, is that the Wilson line is literally measuring it's sensitive to this magnetic flux, and essentially it has to do with the fact that the Higgs field is charged in. So if the Higgs field is charged in, it actually sources a 1/n magnetic flux going through the core. And so the Wilson line is literally measuring 1/n, and that's why when you, so this configuration you can either think of as the vortex seeing the Wilson line, or it's more like, I'm getting better at drawing. It's more like the Wilson line can detect that there's a magnetic flux running through its loop, and then when you unlink it, it realizes that there's no flux going through the loop, and that's how the action works. So that's the physics of what's going on here. And the reason why this gives you as the n-gauge field is you say first what you can do is you can rewrite it I n over 2 pi A1 which dB2. So dB2, so B2 is, A1 is a U1 field, a gauge field, and this is also a U1 gauge field because phi is a periodic scalar, so everything's U1. And what that means is that the integral of B2, dB2 over 2 pi on any closed manifold is integer value. So what you can do is you can split the action like this, looking at it in this form, you would say A1 wedge, or maybe just times, dB2 over 2 pi. So this, when you integrate this over some closed foliation of your manifold, you get I n, we'll call this K, times the integral of A1. Now A1 we know is 2 pi over, well, okay, so this is what you get when you put in a E1 gauge field. And so now your partition function, after you integrate out B2, looks like the integral over A1, so B to the I and K, where you're sort of summing over all the possible Ks. And so this is literally just looks like a Fourier transform, or a Fourier series rather, with an extra n here. And so usually what you would find is you get, if n was 1 here, you just get a delta function on the integral of A. But with an n, you find that this is actually a restriction on the Hollandes to be Zn value. So essentially the Fourier series in the path integral restricts E1 C1. Okay, so that's all I wanted to say about discrete gauge fields, and I wanted to tell you some applications. Are there any questions? Yeah, what's up?
Can you Higgs further to a subgroup of Zn?
Yes, you can. That when you do that, this story is actually complicated, and I think actually no one's done it. So, okay, you can just close your eyes and do it. It should work. It works totally fine. But the intermediate theory is actually way more interesting because this is a topological theory. But once you couple it to matter, it's non-topological. It's no longer topological. And so you can still you can still do this story where you have some one-form symmetry and you make some topological operator. But this is going to be very different. It's going to be addressed by actually it's going to be addressed by a three-dimensional surface. But anyways, the dynamics of that theory is, I think, maybe potentially interesting and unknown.
Be a multi-step process, right? So here you're going from U1 to Zn.
Yep.
Then you're just starting with Zn to get some subgroups. So it's the mechanism is going to be different, right?
I don't think the mechanism will be different, but the intermediate physics might be interesting. I think that's all I mean. It's going to be kind of like flux attachment and like the quantum Hall effect. Yeah. But I don't think people have thought about this in a four-dimensional theory all that much. Okay. Yes. Oh, sorry. Okay. Cool. So yeah. So anyone who goes into research on higher form symmetries, BF theory is one of your best friends, or your worst enemies, depending on how things are going. But anyways, this is how we describe pretty much all sort of gauging of a Zn symmetry. So this is a gauging of a Zn zero form symmetry, because it is a Zn zero form gauge group. But it's also how we describe turning on, well, it's one way you can describe turning on one form symmetries, because you have a Zn one form symmetry here. And so, I guess I have one more comment. So more generally, if you have some d-dimensional theory, and you want to describe a Zn P form, and if you have a Zn P form symmetry and you gauge it, then you get sort of a more general BF action, which is essentially the same, except you just change the dimension of everything. So now for a P form symmetry, you have a P plus 1 form gauge field, and then the corresponding B field will be a D minus P minus 2 form field. And then everything I said just follows directly by changing all of the dimensions and codimensions, and that's the beauty of differential forms. You only have to do things once, and it works in all dimensions, roughly. Okay, cool. So, yes, are there any questions? Okay, cool. So now I'm going to tell you two examples of how you can use discrete symmetries to study interesting problems. And for both of these, So the first one is going to be in just pure non-abelian Yang-Mills theory. And the second example is going to be QCD. And by QCD I mean I'm going to take SUN gauge theory plus one Dirac fermion in the fundamental representation. Okay? I think that should work. Okay, so.
One question. So you can do all of this for non-abelian discrete groups also, right?
Okay, yeah. So the first caveat is that you can only have a discrete gauge field if you're gauging a discrete zero-form symmetry. So that's the first caveat. The second is that actually there's no known Lagrangian description of a discrete gauge field except for the Zn gauge fields and for dihedral groups. And the reason why you can do it for dihedral groups is that dihedral group you can write as Zn semi-direct Z2. And so essentially you just have a Zn and a Z2 and then you give it some funny relations. But for example, the alternating groups, there's no known description in a continuum Lagrangian. Okay. All right, so the first example, we're going to take SU and I'm going to see, I guess, gauge theory in 4D. So this is based on a paper. Oh, sure. I'm going to run particularly this spot. Okay. I'm going to list the authors that I remember, which is always better. So it's Komar-Godsky, Seiberg, Gallardo, and I believe it's Willett. And there might be other people, unfortunately, that I forget about, and I apologize to those authors. And this paper is often called the TPT paper, which stands for theta, time reversal, and temperature. And it was really the first application of these higher form symmetries to derive something new about physics, although we sort of already knew the result from other things. So, right, so as I said, we're starting with 4D SUN gauge theory. So here we can write the action 1 over 2g squared, and then trace of f squared. And so this is the standard action you would write down. But there's an additional topological term you can write down, which is called the theta term. So it's given by this, f wedge f over 8 pi squared. Okay, so this term is topological because, again, it only has wedge products and exterior derivatives, and so there's no dependence on the metric because there's no Hodge star. So this is a topological term. And another way to see it's a topological term is that when you turn on theta, it doesn't change the equations of motion. So this is another way to see it's topological because it doesn't change the propagating degrees of freedom. Okay, so now we need the fact that for an SU1 gauge field, the instanton number is an integer. Okay, so theta here is a parameter of your theory. So you can think of your partition function as being a function of that parameter. So since this is an integer, right? So when you get sum over the fields, the gauge fields in the path integral, you sum over all the possible different integers. But the fact that they're all integer implies that the partition function is invariant under shifting theta by 2 pi. In other words, this. Okay? But now, we want to look at higher form symmetries. So something we mentioned, we talked about yesterday, is that S2N Yang-Mills theory has a one-form center symmetry. And what this does is this corresponds to the fact that the Wilson line in the fundamental representation is protected because the only charged matter in this interacting theory are gluons, which are in the adjoint representation. And essentially, the point is that if you take n of these, this gives you something which is like the Wilson line in the adjoint representation, which can be screened by gluons, which are in the adjoint representation. So this is the statement of the one-form symmetry in Yang-Mills. And as I keep saying, the most important or the most interesting thing you could do is try to turn on a background gauge field. So now that we're experts, we can turn on a Zn background gauge field, which I'll write as B2. And really, you should think of this B2 as similar to this B2 over here. So B2 is a gauge field which is, we can just call this a U1 gauge field, which has this Zn restriction that we talked about. Good. And so the restriction is that B2 over 2 pi is 1 over n quantized. Because B2 is not a field strength, it's a gauge field. So it's allowed to be, so it's essentially valued in Zn. Okay. So one of the things I tried to emphasize yesterday is that when you turn on the background gauge field for a center symmetry, you change the quantization of the instanton number. So now this trace f wedge f great I squared is going to be quantized as n, so integer plus n minus 1 over 2n times b2 wedge b2 over 4 pi squared. So this 4 pi squared just comes from the fact that this is 2 pi quantized, or its integral over 2 pi is quantized. So that's just to take care of that. So essentially the point is that this can be valued in 1 over 2n times z. Okay. So that's cool. We haven't really done anything yet. But now we see that the partition function is no longer, so now we see that theta is no longer 2 pi periodic. Rather, theta is, it's going to be 2 pi n periodic. So if we shift theta by 2 pi times little n, this is going to be z of theta times e to the little n times n z minus 1 over 2n times integral b2 at b2 over 2 pi.
So n and c are the same here?
Yes. Sorry. Okay. That's right. So, okay. There's actually a little trick here that I've been glossing over, and I don't think we have time to explain it. So I'm going to continue glossing over it, or I'll tell you that I'm glossing over, but I won't explain why. So on a normal, and by normal I mean a manifold where you can put spinors, put fermions, this is even. So if you multiply it by nc, then you get something that's integer valued, so that you can see the that the whole term is 1 over nc, that 1 over 2 nc value. So sorry, that's what I meant to say. Okay, good. Cool. So Jose might say otherwise, but I would claim that this is not actually a symmetry of your theory, so that's fine, who cares? But a nice symmetry of a lot of quantum field theory is time reversal. And this acts by sending trace f wedge f to minus itself. And so what it means is that this effectively sends theta goes to minus theta. And so if theta is non-zero, this is usually not a symmetry. However, we know that when we don't have a one-form symmetry, their theta is 2 pi theta out. So that means that you have a time reversal symmetry when theta is 0, because 0 goes to minus 0 is itself. And theta is equal to pi. Because if you shift theta goes, because the action taking pi to minus pi is equivalent to itself mod 2 pi. So pi goes to minus pi, and you can add 2 pi to 3. So there's a classical time reversal symmetry at theta is equal to 0 and pi. Cool. So there's a one-form symmetry, that's a time reversal symmetry. But now what you can see is that there's going to be an anomaly between the two. And the reason is that we had to use the periodicity of theta in order to show that theta time reversal is a symmetry at pi. Here, it is not a symmetry when you turn on a one-form background. So if you turn on RB2, and theta, go to theta is equal to pi. And now I'm going to look at the action of time reversal on the partition function. This goes to minus pi. And now we use this equation, which I only partially boxed, to show that this is equal to z of pi times e to the nc minus 1 times nc to u2 with u2 times pi. Oh, that was fine. 2 pi times I. And following, sort of unraveling all of the notation, this is z of n value. So this is an anomaly. So what did we learn? So anomalies are good because they tell us that theories, the anomalies have to be matched between a UV theory and an IR theory. Yang-Mills theory, SUN theory, is thought to confine when it flows to the IR. So one of the, what do I mean by confined? What I mean is that there are no propagating degrees of freedom in the low energy because there's a mass gap. There's a mass gap, which is the confinement scale. And to prove this would give you, I think it's $1 million, it used to be $1 million US, but I feel like that's not very much money anymore. But anyways, this is one of the Millennium Prizes. If you can solve for this mass gap, then you win. You win at physics. You're like the most important physicist since, I don't know, who's the most important physicist? You'd be more important than Einstein, I think. Well, that's debatable. You'd probably be more important than Newton. Good. So what we can do is we can try to make a phase diagram here. So imagine this is your energy scale. So we're starting up here, This is our T, this is where our UV scale is, TE. And we want to look at it as a function of theta. So this is, here's the point, here's the point of pi, and here's the point theta is equal to 0. So,
Daniel,
yes, sir.
I just want to come back to one question that Isabel asked, I think, in the first lecture.
Yes, please.
It was, so when you don't add that background gauge field, this is a symmetry, right? This time reversal is a symmetry. So is time reversal now anomalous in the theory or not, even without the background gauge?
Oh, good. Yes. So I would say that it is a symmetry. And essentially what the point is, okay, I think this is the correct interpretation, although I've never actually thought about it this way and I'm not sure. I think what's happening is when you turn on this background field strength, you can think about, there's two ways you can realize time reversal symmetry and infrared. One is that your ground state is invariant under time reversal, and the other one is when you have a Kramer's doublet, which means that there's just two states that are exchanged by time reversal symmetry. I think what's happening when you turn on this background gauge field, you're breaking time reversal symmetry. And I think essentially what's happening is, well, I don't know if you think of it as giving I think essentially you're introducing a relative phase between these two states. And so they're no longer exactly related, they're related by a phase. So it's kind of like saying you've broken symmetry, except it's a very mild version of breaking. It just allows you to detect the fact that there's a Kramer's doublet in the infrared.
I see.
Right. So essentially, that's exactly what I was going to say here is what the different interpretations are. So you can imagine that we're only really allowed to track, or it's only easy to track the RG flow at either theta is equal to 0 or pi. And everywhere else, there's sort of not an extra symmetry. There's no time reversal symmetry, so we don't really know what happens. But it's believed what happens is that at theta is equal to pi, sorry, this is provable. This is essentially what we're just proving now, is that at theta is equal to pi, the theory cannot just totally confine to a trivial theory. You can still have a mass gap, but you have to have at least a degenerate ground state. So at theta equals to pi, the infrared theory is at least non-trivial. There's sort of two ways you can do this. One is that you have some topological phase of matter. In other words, you just have some topological quantum field theory. For example, like the BF theory that we've written down. And the other one is if you have some sort of gapless theory, which you can either it could be some sort of exotic phase of matter, or it could be just that the theory doesn't confine. It's believed, I think, that it's a topological phase. And then everywhere else, we can't really say anything else. It's sort of thought that everywhere else, the theory is confined in the normal sense that there's no ground state degeneracy. And then just at theta is equal to pi, there's some sort of transition. So it's often said that there's, I believe there's a large N computation that shows this, which by that I mean if you take the size of the gauge group to be very large, there's a lot of simplifications you get in quantum field theory. And so the idea is that there's sort of two states, and there's a mass gap between them. And what happens is as you change theta, they sort of get, the gap becomes smaller and smaller, and then at theta equals to pi, they're exactly degenerate, and then they sort of switch which one's the vacuum. And so that's what's thought to happen in super Yang-Mills theory. And what we just showed is that at theta is equal to pi, well, we proved that theta is equal to pi, there has to be some sort of degenerate ground state.
But you're saying it's twofold degenerate.
Yes.
So it doesn't depend on this NC, because I was just naively thinking that because you have a Z2 MC, what role does the NC play?
good. So it's at least Z2 degenerate. Right. That's not as nice, but I don't actually remember what the statement is. I know you can. I know this anomaly proves that at least it's a Z2 because there's sort of only a Z2 anomaly. I think that means essentially there's a counter term that you can put in that reduces this anomaly. So instead of being Z2 and C, it's actually Z2. I think that's probably true, except maybe when NC is itself even. There's some like weird number theoretic issues, but all I can say to you is that we showed that there's at least a Z2 here. And so this is one of the strong statements you could derive using generalized symmetries, is that confinement is not as simple as you might naively think. So I think this is probably a good place to stop. So.